Welcome. So glad that you all are here. Here we go. So we are taking a look at water and oceans, and we're going to use this context to think about concentration and solubility, but at a much larger scale. So when you see this image, what do you notice? What stands out to you?
The Atlantic Ocean is really salty.
Yeah, it is. It's one of the, if not the most salty oceans. What else do you notice? What's the least salty?
Northern parts,
Yeah,
kind of, or the Pacific Ocean.
yeah. So parts of the Pacific Ocean and right closer to um Canada and then looking at Russia and parts of um Asia. So the oceans that are off there have that much lighter sea surface salinity. What about our scale? So what is a PSU? Does anyone know what that is? Okay, a pause is a good thing. That means there's something we don't know yet, and we're going to learn more about it in our time together. Notice there are a couple of lakes that actually have an incredible level of salinity. So the Dead Sea is an example, and you can see that here. We're going to take a look at how you measure salinity and what PSU is. So uh, salinity is usually measured in parts per thousand. It's also sometimes measured in practical salinity units or PSU. And I think it's hilarious that um, we we call it practical salinity units, but I guess it's a good indication of 1 part per thousand is equivalent to 1 PSU. So I think this is a really great example of sometimes we use units depending upon our discipline or the convention in the field. And so if you are an oceanographer, you think of it in PSU. If you're a chemist, you're thinking about it in parts per thousand, but these units are equivalent. So what does that calculation actually look like? Well, we have grams of salt per kilogram of seawater. So if we were actually setting that up, it would be 35 grams of salt. And you might be wondering, well, what salt? We're going to talk about that in just a moment. Per 1,000 grams or 1 kilogram of seawater. And interestingly enough, when they report this, usually, right, they multiply it by 1,000, so it's literally just this top number. That's a useful piece of information. So, um, if you're trying to approximate it, you can often just take a look at the amount of salt, and that ends up being your parts per thousand. Um, Sometimes folks like to talk about this in terms of percentage, and this here is a weight percent or mass by mass. So mass of salt um, so that's another way that we can also refer to our salinity, although it's less common. I think most folks gravitate towards PSU if you're in marine science and parts per thousand if you are a chemist or a biologist. Okay, so that's our introduction to salinity and our initial connection with our concentration or chemistry. Let's take this a step further and look at our sea salts. So take a moment and look at this visualization. What else do you notice? So
A lot
technically,
of different salts.
yeah, there are a lot of different salts. In fact, right, if we think of the salt, so that calculation that we just did of 35 grams, right, and this is a visual that represents the amount of salt per the amount of 1 liter of water. If we think about the composition of that salt, over half of it is chloride, so the anion. And then we have a little bit of sulfate, which is also an anion. And then most of the cations are sodium, but we have some magnesium and we have a little bit of calcium and potassium and some other minor constituents that we group together, at least for the purposes of this visualization. So when we're thinking about the concentration, we can get a lot more specific. Say, for example, the concentration of chloride in seawater, the concentration of sodium in seawater, and figure out what that is. Obviously, to do that, right? If we were thinking about a concentration calculation or a part per thousand or a part per million or a part per billion, depending upon the size, we would need to, right, think about the molar mass of our ion. We need to think about the volume that that ion is in, and then we could do a concentration calculation. Okay, so we're going to do a little bit of that, and we're going to think about using our parts per thousand calculation, but realize that, right, as scientists, we're nuanced. So we realize that not all water is the same amount of salt. The convention is to refer to really salty water as briny water. So, what would be an example? Well, the Atlantic Ocean, from that image that we first looked at, you identified as the saltiest of the oceans. So, why is the Atlantic Ocean saltier than other oceans in the world? Well, there's a couple of reasons for that. So there's a much higher evaporation rate for the Atlantic Ocean, in part because of its position relative to the sun. There's also, and maybe this is more key, limited numbers of large rivers that are feeding into it. So there's less fresh water, which is why it tends to be more concentrated. Then there's also something that is known as the global conveyor belt effect, which I think the technical term for this, if you're a marine scientist, is the Atlantic Meridional Overturning Circulation, or AMOC, which means there's salt water from other oceans that come into the Atlantic Ocean. But if we're thinking about, right, really briny water, the briniest of the water would be in the Dead Sea. Now, that's technically not an ocean because it's surrounded by land, but we're going to use that as our example calculation here. And I think maybe the most important piece that we want to recognize is that, let's say we had 34.2 grams of salt, and this is in the Dead Sea. Well, what does that mean relative to the amount of water? Well, if that was per 100 grams, of water, how would I get it to the calculation that I need, right? Because I need 1,000. So I can set this up as a ratio, just like what we've done before. So if I had 1,000 grams of water, or 1 liter, I could calculate the amount of salt that I would need. Ooh, that's a terrible line that I just, let's see if we can fix that line. All right, one more time. All right, so I need to know the amount of salt. Well, in this case, it's moving a zero by one place. So it would be 342 grams of salt per 1,000 grams of water. Which, if we think about that, right, given our calculation, so that would be equivalent to 34 0.2 parts per thousand. Right, which is quite salty. In fact, it's so salty that it changes the density, which changes the buoyancy, which is why if you were to go and visit the Dead Sea, you would float. It would be impossible for you to sink in the Dead Sea. So maybe one of the things that's important for us to think about is this range. So the Dead Sea can be up to 40 parts per thousand. Um, there are, though, saltwater pools that are artificially created or brine pools that sometimes occur naturally that can have 50 plus parts per thousand. But this is an example of something that's quite salty if we're looking at the Dead Sea. There are other places that also have a high level of salinity. So the Mediterranean Sea is another example. The Atlantic Ocean, right, is our saltiest. And so we could do a calculation, right, of the concentration based on that. But I want you to notice that there are places in the world that are minimally salty. So the Baltic Sea is a good example. It's 8 parts per thousand. And intriguingly enough, there are actually legalized limits on the amount of salt that can be in water when you're irrigating agriculture. So, locally in Monterey County, one of the concerns that we have is saltwater intrusion into our groundwater. And the reason for that is because if the salt concentration goes above 2 parts per thousand, then it can no longer be used to irrigate crops. And, right, it's useful. We always need a reference point. Our drinking water has only 0.1 parts per thousand. So this PPT is really a valuable measure to help us understand the concentration or the amount of salt that's in water. Okay, so we have a reference point. Well, let's see if we can take this a step further. So both temperature and salinity affect our density. So the more dissolved salts that there are in a body of water, the greater the density of that water. So if the density and the temperature of a water sample are known, then you can actually calculate salinity from a graph. So it won't surprise you to know that sometimes it's a lot easier to measure density or temperature than it might be to measure salinity. And so what we have on the left essentially is a graph where if you know two of the three variables, you can find the third. So for example, if I knew the temperature was 25 degrees Celsius and I knew the density was, right, 1.020 or less, right, then I could look on that curve and determine the percent or the part per thousand. If I wanted to convert it to percent, I could do that, of the salinity. So the really valuable part here is to know that, okay, I have a couple of different ways that I can measure this. And so there are tools that essentially allow us to measure the density really easily. And that can then, with this table, inform our knowledge of salinity. So these are a couple of the tools that you could use if you were measuring salinity out in the field and you didn't have the ease, say, for example, of calculating concentration. All right, so it's not just, though, the salt that we're interested in when it comes to the ocean. We're also really interested in the concentration of total dissolved inorganic carbon. This DIC, or another way of saying that is the sum of the concentrations of three coexisting species. So we're going to unpack this a little bit. So this idea of dissolved inorganic carbon, or DIC, is the sum of three species. So we have our bicarbonate ion, so that's HCO3 minus. Our carbonate ion, that's CO3 2 minus. And then our carbon dioxide, or CO2. So if we think about this, right, it's a relatively small amount. So 2 millimoles per kilogram. And 90% of that is going to be our bicarbonate. Only about 10% is our carbonate. And then less, right, than 1% is our carbon dioxide. And the reason this is going to matter is because we're going to talk about dynamic equilibrium. And so each of these species or chemical components plays a critical role. So let's talk a little bit more about what that role is. Before we go further, I want to note that there are physiological units that we measure associated with mammals, the human body, and then there are the equivalent marine science units. So typically for pH, we're looking at a total scale, whereas for physiology, it's usually an abbreviated scale, usually one supported by the National Institutes of Standards. You'll notice that when we're talking about carbon dioxide, we're really talking about partial pressure. Whereas I think sometimes in human physiology, there are multiple measures that we could use, although microatmospheres is appropriate for most of the units that we're going to be talking about. Then we have the solubility of carbon dioxide. So we talked about KSP last time for solids, but there's also solubility for gases, and we're going to talk about that. And then dissolved inorganic carbon, or DIC, that was what we were just talking about, is typically measured in moles per kilogram for marine science, whereas for physiology, it's in moles per liter. And then we think about our concentrations, and again, we use similar but slightly different measures. So the moles per kilogram, remember, is molality, whereas the moles per liter is molarity. So again, this is kind of the convention of the discipline or the field of study, and it's important to know the distinctions between the two. We're going to come back to this in just a minute, but it's a nice reference table for you. Okay, so I want you to take a moment and think about why the concentration of ions matters in the ocean. So think of one or two examples of why the ions that are present in the ocean could matter. Like, why do living organisms need those ions? What do they do with them? What do you think? Why are those ions essential?
Carbonate to make shells.
Yeah, right. So we use the calcium carbonate to actually make either the outer or the inner support structure for organisms. And we also know that ions are really critical when it comes to, say, for example, chemical signaling, the exchange of water we talked about in terms of tonicity. So those are just a couple of spaces where ions matter for equilibrium. The other piece that we want to think about here is these are all going to be influenced by pH. So sometimes when you're having this conversation, it's really the use of the word alkalinity in the field. Sometimes folks will refer to it as acidity. Sometimes folks will say the acid or base. And sometimes folks will just refer to it as the effect of pH. But when we say that, what do we mean? Well, if you have an excess of proton acceptors over proton donors, and so if we think about our generic, right, we've used HA plus a base which we'll refer to as B. That's going to form our conjugate acid, or HB, and our conjugate base, A minus. So in this situation, if you have an excess of proton acceptors, so that would be the base, over proton donors, that would be the acid, right? That's going to shift our equilibrium. So it plays a significant role in ocean chemistry and in buffering. And we're going to look at the example today of calcium carbonate precipitation and dissolution. And when we're talking about the dynamics, we're going to say, well, pH can influence the quantity of ocean carbon dioxide uptake. And that's going to be influencing not just temperature, but a variety of other factors too. So let's talk a little bit about that dynamic equilibrium. So if you want to, right, and you're looking at this equation below, this is technically two reactions that are combined. So we have the synthesis reaction of carbon dioxide and water forming carbonic acid. So we can label that. That's going to be an HA. And so when our HA reacts, it's going to form bicarbonate. That's what this one is referring to. Oh, sorry. Let's change the color. So bicarbonate in this case would be the A minus that is being formed because it has given up one proton. So let's actually draw out that equilibrium because it's going to be helpful for us to see. So we have our H2 CO3 that when it reacts is going to give up an acidic proton, so it's going to form H, and that H plus can be associated with any kind of base, plus HCO3 minus. So notice this is our HA, and this is our A minus. But you'll also notice that HCO3 can go on to react. So HCO3 minus still has a proton to give up. And it forms the conjugate base, which is the carbonate. So notice, as long as there's an ionizable proton, something can be considered the acid, right? And in this case, we have, right, an equilibrium that's influenced by multiple chemical species. So if you want to think about our model, we have CO2 that's coming into the ocean from the atmosphere. That combines with water and creates carbonic acid. But this has a pKa of 6.3, which means that in the ocean, this H2CO3 doesn't stick around. In fact, it's going to deprotonate to form, it will give up one of its hydrogens, and it's going to form this HCO3 minus. Now, the deprotonation of HCO3 minus to form carbonate has a pKa of 10.3. So my pH has to be above 10 in order to form my carbonate ion, which tells you why the predominant species that we see in the ocean is going to be this bicarbonate. Because rarely, right, does our pH go below 6.3, in which case this would be protonated. And rarely does it go above 10.3, in which case we would deprotonate and form the carbonate. So most of, in fact, that's the 90% that we just talked about, of the bicarbonate ions in the ocean, right? That's the form that equilibrium favors. Now, we can always shift equilibrium by changing temperature or changing the pH, which then changes the concentration of that chemical species. So this is going to be the basis for a lot of the conversation that we have today. And actually, since we're thinking about buffers, it's going to be critical for the next pattern of inquiry that you're going to take a look at. So I'm going to pause for just a minute Any clarifying questions about the equilibrium reactions that we're looking at, either for carbonic acid going to bicarbonate or for bicarbonate going to carbonate? Okay, hearing none, if you have questions, please don't hesitate to pause me. But we're going to move and take a look at the next piece of this. So, I often ask you to write claim evidence and reasoning statements. We're going to work on one together today. So, we know the ocean plays a major role in global carbon cycle and the storage of anthropogenic or human-made carbon dioxide. So, this really key function of the ocean is related to its ability to dissolve carbon dioxide with water and to form bicarbonate, what we were just taking a look at. And, right, these minor quantities of carbonic acid and the carbonate ion. So, alkalinity, or the excess of bases, is what governs the efficiency at which this occurs and provides some buffering capacity towards acidification. So, today we're going to be talking about ocean acidification. Well, why does that matter? Well, the ocean is what attenuates the increase in atmospheric carbon dioxide, and that's going to play a role in global warming. And it's related to this very large volume and surface area of the ocean and the reaction of dissolved carbon dioxide in water that then forms carbonic acid and the resulting conjugate bases of bicarbonate and carbonate, which aren't directly exchangeable within the atmosphere. So a good way of thinking about the ocean is as a sink. So whichever ocean you want to imagine, we're going to draw that as a sink. And the reason for that is, you're going to have to forgive my faucet. So there are many sources of carbon dioxide. Some of them are naturally occurring, some of them are man-made. But the ocean is a sink that absorbs that CO2. And the reason it can do that is both because of volume and because of its surface area. So if you had a deep volume but minimal surface area, it would be harder to absorb atmospheric CO2. But because of how significant the surface area is, it is very effective at absorbing the CO2 from the atmosphere. Now, we're going to take a look at and start to think about, for the purpose of our claim evidence reasoning, how you can influence that dynamic equilibrium. So here's a different visual representation of the carbon dioxide in the atmosphere and the ball and stick drawings associated with, right, dissolve CO2 and water, and then the carbonic acid that's formed, and then the transfer or the exchange of hydrogen ions between carbonic acid, bicarbonate, and the carbonate ion. So you're going to notice that there are multiple ways that you can make bicarbonate. And that's going to be a key piece of information. We're going to take a look today at buffer calculations. And we're going to think about, right, the seawater that's absorbing carbon dioxide from the atmosphere, the reaction to form carbonic acid, and then the exchange of hydrogen ions to form bicarbonate and carbonate. So each of those chemical species are going to be critical to the buffer calculations that we do today. So we're going to come back to this in just a moment. But before we do that, I want to talk about something called the Ravel factor. So this is actually a measure of the ocean's buffer capacity for carbonate in seawater, or I suppose you could calculate it in freshwater too. So it's the ratio between the change in the partial pressure of carbon dioxide relative to the fractional change in dissolved inorganic carbon. So if you recall, right, we talked about dissolved inorganic carbon as a measure of the amount of carbon in the ocean. So a couple of pieces, right? This equation is at constant temperature. It takes into account salinity and total alkalinity, oftentimes referred to as Ta. So the higher the Ravel factor, the lower the ocean's buffer capacity, the faster the change of the partial pressure of carbon dioxide in the ocean at a given DIC. So this Ravel factor is also a really good indicator of how the ocean buffers relative to pH. So we're going to write a claim evidence reasoning statement about this big idea. So when I need to dissolve carbon dioxide, that's going to be governed by multiple equilibria that occur at the same time. So they're co-occurring. So it's the equilibria between carbonic acid and bicarbonate, between bicarbonate and carbonate. So 19 out of the 20 molecules of carbon dioxide entering the ocean get converted into bicarbonate. And the total amount of dissolved inorganic carbon in the ocean is typically about 200 times that of the dissolved carbon dioxide. So we have much more dissolved inorganic carbon than we have dissolved carbon dioxide. So the equilibrium really favors dissolved inorganic carbon. When we're thinking about doing a calculation, then we have to think about Le Chatelier's principle. So I want you to take a moment and hearken back to the distant past and think about general chemistry or biochemistry or a course that you took where you thought about equilibrium, and tell me in your own words, what is Le Chatelier's principle? How would you describe that for someone else? If you were in the grocery store and someone suddenly turned to you and said, do you remember what Le Chatelier's principle is? What would you say? What do you recall?
I kind of remember it as like if you change certain factors like concentration, temperature, and pressure, the equilibrium will shift appropriately to react to that.
Yeah. So if you change concentration or the pressure or the temperature, then the reaction shifts to obtain equilibrium. That's a great working definition. So if we think about, say, for example, changing the concentration. So if we think about a simplest case scenario, so in my simplest case, I'm going to have my reactants, and I'm going to have my product. If, as I'm forming my product, I take it away, then, right, more of my reactant is going to shift to form product. So this is a way of saying that when you have a stimulus, there's a response to that stimulus. So let's take a look at that definition. So I think this is fascinating. So in 1888, Le Chatelier gave this statement of a principle he had been thinking about 4 years in time. So every change of one of the factors of an equilibrium occasions a rearrangement of the system in such a direction that the factor in question experiences a change in a sense opposite to the original change. Now, I don't know about you, but I think that's a statement that could bear from some refining, right? It's pretty complicated, and I'm not sure that, right, it says it as clearly as it could, but it's a great beginning. Another way of saying this is similar to what Jackie shared. If a stress is applied to a system at equilibrium, then the system readjusts, if possible, to reduce the stress. Or another way of saying that is, if a system at equilibrium is subjected to stress, the equilibrium will shift in an attempt to reduce the stress on the system because equilibrium is the desired state. All right, so let's think for a moment about what those changes could possibly be. So we referenced concentration. It could be an increase in concentration or a decrease in concentration. We're talking about temperature, so that could be temperature going up or down. We could think about pressure changes, so that could be lowering the pressure by increasing the volume, or it could be raising the pressure by decreasing the volume, or it could be raising the total pressure by adding some type of inert or non-reacting gas. And then, of course, you could also change by adding a catalyst, although that's not going to shift the equilibrium. Instead, right, it's going to lower the energy of activation or the barrier to achieving the transition state. So, really importantly, we want to keep in mind that all of these changes would actually be imposed on a system that's already at equilibrium. So, if we think about pH then, right, if we're in a situation where it's low pH, then we have lots of hydrogen ions, right, and only a few hydroxide ions. If it's a high pH, then we have a lot of hydroxide ions and only a few hydrogen ions. And so changing the pH is a great example of a stress on a system. If we swamp a system with hydrogen ions, right, that's going to influence not just the concentration of other components, but it can change, say, for example, the temperature. Now, this is probably a figure that you saw in general chemistry. So a reminder, when we use lowercase p, we're referring to taking the negative log. So for example, pH means the negative log of a hydrogen ion concentration, or pKa is the negative log of the equilibrium constant. And some of these, I think, are familiar to us. For example, the relationship between pH, pOH, and pKw, or the relationship between pKa and pKb. But I recently found, I think, a better version of this representation that I think is a little bit cleaner and helps to show the interrelation. So I want you to take a moment and just follow the arrows. So pick a corner and follow the arrows all the way around the rectangle. These conversions are really intended to help you make sense of changes in concentration. The one we're going to focus on today is the Henderson-Hasselbalch equation, or pH is equal to pKa plus the log of A minus over HA. And we're going to look at that and think about that calculation for bicarbonate and carbonate, or for carbonic acid and bicarbonate. So this is a reference table that I find super useful. There are a great many calculations that this can help with, and it's useful for a variety of different contexts, but this is the space where we're going to focus today. So if we think about that then, one of the things we also want to think about is the relative acid strength. So this pKa equals negative log of Ka, right, has reference values. And we're going to be looking at weak acids. And in fact, bicarbonate is considered a very weak acid. So its pKa, right, is 6.3 for the first deprotonation and 10.3 for the second. So it's important for us to recognize that the acids that we're looking at in the context of the ocean are not strong acids. They're quite weak. So here's where we're going to start. So we know that carbon dioxide is absorbed from the atmosphere into the ocean. And that means that we're lowering our pH. And when we lower our pH, that means we're increasing the acidity of the ocean. And so we have a couple of reference values here, and that's where we're going to start doing our calculation. So before the Industrial Revolution, the pH of the ocean was estimated to be 8.2. In 2013, the measurement was 8.1. So we're going to do two different calculations using our pKa. So I'm going to put those calculations here. So pH is equal to pKa plus the log of A minus over HA. So if I plug in the value, let's say it's 8.2. The pKa value for this change is 6.3. So that's what we're going to put here. And now we're going to solve for the ratio of A minus over HA, which I'm just going to represent as X. So how do we do that? Well, when, right, in your calculator, you're going to take 8.2 minus 6.3, and then we're going to do 10 to the power of 1.9. So if you have a calculator, go ahead and grab that. I would love someone to help me double check my calculations. Okay, so for 10 to the power of 1.9, for x, I get 79.4. Does anyone else agree with that?
Yes.
Awesome. Okay, so let's think about what that number means for just a moment. So this is a ratio of A minus in the numerator and HA in the denominator. Well, I can create a ratio by saying 79.4 to 1. So in the ocean, before the Industrial Revolution, there were 79.4 bicarbonates relative to 1 hydrogen or H2CO3, my carbonic acid. So this is, right, my bicarbonate, and this is my 1, so this is 1 HA to 79.4 A minus, and that's, right, in moles, right? So 79.4 moles of A minus to 1 mole of HA. Okay, so let's see what that value is if we change it, right, from 8.2 to 8.1. Right, so same calculation. Right, so now it would just be 10 to the 1.8. And if I did that calculation, right, x now, I get, so 10 to the 1.8, which is how I resolve my log. So x now is 63.1 to 1. And again, this is A minus or my bicarbonate. to my HA. So if we think about this, what does that actually mean? Well, the calculations that we've just been doing, right, say that when we're dissolving our carbon dioxide, right, there are fewer of the bicarbonate ions relative to the amount of carbonic acid. So it's a more acidic environment. And if we think about the impact that that's going to then have, one example of that impact is on calcifying organisms and coral. So anything that has to use carbonate to build some part of its body, especially the exterior of its, right? So like the shells, for example, or coral is another example. And so when we have this increase in ocean acidification, or this increase in the amount of hydrogen ions, which means there's a decrease in the amount of bicarbonate, that makes it harder to build shells and to keep shells. So that means that the shells are going to be more likely to dissolve, right? And it's going to be much harder, say, for example, for juvenile organisms to be able to build their shells in the first place. So, really interestingly, right, those calcifying organisms are part of our food chain, which means that if they are threatened, then other larger species that eat them are threatened. And that has both an economic impact and a health impact on us. Um, and interestingly enough, there's also some emerging research that looks at chemical signaling. And so there are many marine species that also use chemical signals, say, for example, for egg ventilation is the example that we're looking at here. And so that could have a detrimental effect on reproduction rates. So part of what I'm hoping to show is that by changing the hydrogen ion concentration, that's going to change the buffering capacity that we see in the ocean. And when we change the buffering capacity of the ocean, we're changing the ability to absorb hydrogen ions, but we're also changing the ability of the way organisms function in that environment. Okay, so we're going to do two things that I think will really help as we wrap up. So the first thing that we're going to take a look at, let me stop sharing for just a minute so I can switch to our Canvas page because I want to show you a resource that I have for you. So in the module for this week, you will find two things. So we have an article that I'm sharing with you. So let me share my screen so you can see this. Okay, so we have the pattern of inquiry for solubility that you all know is due on Monday. And then we have our reading quiz. So there are two articles. You get to choose which article you want to do this reading quiz with. The first one is the Flint, Michigan water crisis. But the second one is this ocean alkalinity, buffering, and biogeochemical processes. So it doesn't matter which of these two articles you choose, your call, entirely up to you. But I want to talk a little bit about what the reading quiz is going to look like. So this reading quiz has two parts. And so the goal is for you to create at least 5 sentences to describe what you read in the article. Then your goal is to create 5 questions that you think would prompt discussion. Then you're going to share your 5 sentences and your 5 questions with me. And then I'm going to assign them to someone else in our class. They're going to read that article and respond to the questions. So you're going to choose whichever article is most appealing for you. And then once I get your 5 sentences and your 5 questions by email, I'm going to send them out to someone else in the class for them to respond to based on their reading of that article. So it's 20 points. You get essentially 10 points for your 5 sentences and your 5 questions. And then the other 10 points are for your response to the questions based on your reading of the article. These are intended to give you some choice. So maybe you're really interested in water quality, and so um, reading the Flint, Michigan water crisis appeals to you, or maybe you're in a space where you're really interested in ocean conservation, and so exploring the buffering and biogeochemical processes is what's helpful for you. So that's your choice in terms of our reading quiz. I wanted to show you, if you're like, oh, Sloan, it has been a minute since I have thought about or even entertained the idea of buffers. If you would like a refresher for your recollection, I have 3 examples here that walk us through um, the Henderson-Hasselbalch and how to do those calculations. So if our quick problem solving today left you with questions, or you're curious, or you know you want some additional practice, then I've got some examples here for you to take a quick look at to hopefully help refresh your recollection. So these are with acetic acid and sodium acetate. It talks a little bit about some of the assumptions that we make, which are really helpful as a refresher. And it kind of walks through how to do those calculations. It also talks about why we can make the assumptions that we do and what happens if those assumptions aren't true. And then if you're like, hey, I just want the too long didn't read version, there's a quick summary at the bottom. So hopefully that's going to help as you're kind of revisiting or reviewing or refreshing your recollection on buffers. So we've got a reading quiz that's due on Monday and your pattern of inquiry for solubility. When we come back together, we're going to continue on talking about oceans and buffering. And we're going to transition then to talk about freshwater and the concentration and some of the impacts that are important for our freshwater. So that's what's coming up next week. We have class on both Tuesday, so the 1st of July, and Thursday, the 3rd of July. If, say, for example, you're celebrating the holiday with your family and you're going to be traveling, that's okay. I will always record our sessions and they're available for you. So if you wanted to go back and revisit, say, for example, something we talked about today, you always have access through our YouTube channel. When those videos post is somewhat variable based on YouTube, but you always have access to them. And then the last piece that I want to talk about before we run out of time is this pH scale. So one of the things that we often make as assumptions, and I'm going to open this up full screen. Hopefully you all can see that. All right, so we make the assumption that our pH scale goes from 0 to 14. Well, technically, it can go both below 0 and above 14, but this is a useful reference for a couple of reasons. One, it gives us the pH on the left-hand side, and you can see the color gradient. Those are very common color gradients associated with the universal indicator. But then I think what's actually also helpful is that it also gives the hydrogen ion concentration and the hydroxide ion concentration in moles per liter with an everyday example. And so you can think about both household chemicals, say, for example, the seawater that we talked about today, as a reference point. And so the reason why that's going to be super useful for us is that when we come together on Tuesday, we're going to be doing different types of buffer calculations within the context of the ocean, and we're going to be using pH. So the 2 things that I think will be most helpful for you for doing those calculations are slide 23 from our session today that gives you those reference calculations, and then the pH value. So if you get a chance, please do our exit ticket for this week. That would be super helpful for me because I reflect on what you're learning and making sense of, so I know what to highlight when we gather together next time. If you have any questions, I will happily stay online. Otherwise, I wish you a wonderful rest of your Thursday, and please don't hesitate to reach out if you've got questions.
Thank you.